Hello and welcome back to Return. I'm your AI host, Emmy. Have you ever wondered if the incredible world of artificial intelligence, from your phone's camera to the large language models you hear about, speaks a secret language? Well, in a way, it does. And today we are going to learn two of its most important words: eigenvalues and eigenvectors. Don't let the German roots, eigen meaning on or characteristics, intimidate you. By the end of our journey, you will understand that these concepts are not just beautiful mathematical ideas, but the fundamental tools we use to find stability, meaning, and the most important patterns hidden within complex, chaotic data. You will not only understand what they are, but you will also see how they are the invisible force behind how AI sees and understands the world. So let us start from the very beginning. Imagine you have a perfectly square sheet of a transparent stretchy rubber. Let us draw a grid on it. And at the center of the grid, our origin point, we will draw a few arrows or vectors pointing in different directions. A vector is simply an arrow with a specific length and direction. Now let us define a transformation. A transformation is just a rule for moving things around. Our rule will be simple. Stretch the rubber sheet to twice its original width, but keep its height same. Let us grab the left and the right edges and pull, doubling the sheet's width. What happens to our arrows? An arrow pointing diagonally, say up, and to the right is now pointing in a new direction. It has been pulled more to the right than it has been pulled up, so its angle has changed. It is also longer. A random arrow pointing in another direction will also be skewed. Its directions and length have both changed. But wait, what about an arrow that was pointing perfectly horizontally to the right? When we stretch the sheet horizontally, this arrow gets longer. In fact, it becomes exactly twice as long. But critically, it still points perfectly horizontally. Its direction has not changed one bit. And what about an arrow pointing perfectly vertically? Since we only stretched horizontally, this arrow's length and direction are completely unaffected. It remains exactly as it was. Congratulations! You have just discovered your first eigenvectors. An eigenvector is a vector whose direction remains unchanged when a linear transformation is applied to it. The horizontal arrow is an eigenvector. The vertical arrow is also an eigenvector. They represent the stable or characteristic directions of our specific transformation, the horizontal stretch. No matter how much we stretch or shrink horizontally, any vector lying on the horizontal or the vertical axis will stay on that axis. Now what about eigenvalue? A eigenvalue is the scalar factor by which the eigenvector is stretched or shrunk. It is the measure of how much the eigenvector changes in the magnitude. For our horizontal eigenvector, we stretched it to be twice its original length, so its corresponding eigenvalue is 2. For our vertical eigenvector, its length did not change at all. It was multiplied by 1, so its corresponding eigenvalue is 1. That's it. That is the entire core concept. An eigenvector is an unchanging direction, and an eigenvalue is the scaling factor associated with that direction. Mathematics have a beautifully concise way to write this down. They say that for a given transformation A, a vector V is an eigenvector if it satisfies this equation. Let us break this down without fear. Here, A is the transformation matrix. It is the mathematical object that holds the instruction for our transformation. In our case, A is the set of rules for stretch horizontally by a factor of 2. V is our eigenvector, the special arrow whose direction does not change, and lambda is the eigenvalue, a simple number that represents the scaling factor. Look at the equation again. It expresses a profound duality. The left side, A, represents a potentially complex operation. The matrix A could represent a stretch, a rotation, a shear, like pushing the top of deck of cards, or combination of all three. Applying A to a vector V can be a complicated geometric process. The right side, lambda, times V represents a trivially simple operation. Just take the vector V and scale it by a number lambda. make it longer, shorter, or flip its direction if lambda is negative. The eigenvector equation is a puzzle. It asks, for a given complex transformation A, can we find any special vector V where the transformation's effect is identical to just simple scaling? And the solution to that puzzle is the set of eigenvectors and their corresponding eigenvalues. Think of the Earth spinning on its axis. The rotation of Earth is a transformation. Every point on the surface is constantly changing its position and velocity vector. But what about a vector pointing from the center of the Earth to the North Pole, right along the axis of rotation? As the Earth spins, that vector stays put. Its direction is unchanged. It is an eigenvector of the rotation, and since its length doesn't change, its eigenvalue is 1. A neat mathematical trick, right? But the question arises, what is it for? The true power of eigenvectors and eigenvalues comes to light when we deal with data. Let us imagine you are a real estate analyst. You have a data set of 10,000 houses, and for each house you have 500 different features: square footage, number of bathrooms, distance to the nearest park, average neighborhood income, crime rate, air quality, age of roof, and so on for 193 others. Your goal is to understand the main factors that determine a house's price. But how can you possibly visualize or make sense of 500 dimensions? Our brains can handle 3, maybe 4. This is known as the curse of dimensionality. And this is where principal component analysis, PCA, comes in. PCA is a technique for reducing the dimensionality of data, and it is powered entirely by eigenvectors. So the problem is we have 500 features which are likely related. For example, square footage and number of bedrooms, they are not independent. Bigger houses tend to have more bedrooms. This relationship is called covariance. So what we require is a relationship scorecard. We can compute a giant matrix called the covariance matrix. You can think of it as a big table or a scorecard. For every pair of features, example square footage versus number of bedrooms, crime rate versus distance to park, it gives us a score how they vary together. A big positive score means when one goes up, the other tends to go up. A big negative score means when one goes up, the other goes down. And next comes finding the principal components. Here is the magic. This covariance matrix is a transformation matrix. Just like our rubber sheet stretcher A, it describes the shape of our data cloud in 500 dimensional space. If we find the eigenvectors of this matrix, what do they represent? They represent the fundamental axis of variation in the data. The eigenvector with the largest eigenvalue points in the direction where the data is most spread out. It is the most important story in the data. This is the first principal component. For our housing data, this primary eigenvector might be a combination of square footage, number of bedrooms, and neighborhood income. We could give this new combined axis a name: overall affluent size. The eigenvalue for this eigenvector will be huge, telling us that this component explains a massive chunk of the variation in housing prices. The eigenvector with the second largest eigenvalue points in the direction of the next most significant variation, and it will be mathematically guaranteed to be orthogonal, that is at a right angle to the first. Now this might be a component we could call urban versus suburban, a combination of low crime rate, good air quality, but far from city center. By finding these eigenvectors, we find the natural axis of our data. We can then decide to only keep 2, 3 or 10 principal components and discard the rest. We have reduced our 500 confusing dimensions to a handful of meaningful ones, losing very little of the important information. We have cast a shadow of the 500 dimensional object onto a lower dimensional wall, and we used eigenvectors to find the perfect angle to shine the light from, so the shadow is as informative as possible. See the plot generated by this code. You could see a cloud of data points. The first eigenvector, the red arrow with larger eigenvalue, would point straight through the longest axis of the cloud, capturing the main direction of the variance. This brings us to the cutting edge. How does this relate to AI like ChatGPT or Gemini? These models work by turning words and concepts into vectors in a phenomenally high dimensional space, often thousands of dimensions. And this is called an embedding space. In this space, directions have meaning. The famous example is that the vector operation, If I have a king vector, I subtract from it a man vector and I add a woman vector, it should result in something very similar to a queen vector. Now imagine a transformation within this space. A transformation, that means make this concept more formal. If you apply this transformation to the vector for a buddy, it might shift it towards friend and then to a colleague and finally to associate. The vector changes directions. But what if you apply this, make it more formal transformation to the vector etiquette? It is already a very formal concept. It might just get more formal of what it already is. It might scale along its own direction, but it won't point somewhere new. In this abstract sense, etiquette could be an eigenvector of the formalizing transformation. Researchers are now actively studying the matrices inside these giant neural networks. By calculating the eigenvalues and eigenvectors of these matrices, they are trying to understand the model's internal geometry of thought. Some early research suggests that the distribution of eigenvalues might change when a model is hallucinating, that is, making things up, versus when it is stating a known fact. The shape of the internal state described by its eigenvalues could be a clue to the model's confidence or factuality. Now it's your time to think. We have traveled from a simple rubber sheet to the frontiers of AI. The core idea remained the same. Eigenvectors are the stable directions that characterize a system's transformation, and eigenvalues tell us the magnitude of change in those stable directions. They are the scaffolding upon which much of the data science, physics, and AI is built. To test your intuition, ponder upon these questions. Imagine a transformation that squishes everything to half its original size uniformly. What would the eigenvectors be? What would the eigenvalue be? Think about which arrows wouldn't change direction. Can an eigenvalue be negative, for example -1? What would that mean for the eigenvector? What would a transformation with an eigenvalue of -1 look like? Next, what if an eigenvalue is 0? What happens to the eigenvector in that direction? Imagine sliding the top of a deck of the cards to the right. The top card moves the most, the bottom card doesn't move at all. This is a shear transformation. Can you guess which vector direction would be an eigenvector? The secret language of AI isn't so secret after all. It is the elegant language of linear algebra, and now you understand two of its most powerful words. The next time you see a complex system change, ask yourself, what is staying the same? You might just be looking for an eigenvector. Thank you for joining me on Return. I'm Amy. See you next time.